Great. Hi, good morning again. So, um, here I'm going to introduce a recent AGU monograph volume, like in studies therein, synthesizing EarthScope results from Alaska and Northwestern Canada. And I'd like to acknowledge two co-editors on the volume, Natalia Rupert and Jeffrey Fremuller, and Natalia is the lead on the volume. So again, we're stepping out again, Pacific Ring of Fire, that's an area of interest of mine. And as a geodynamicist, all roads through any models or like any road to the models is always through the data. And so I was, having worked in Alaska for some time now, I was really interested in being a part of synthesizing these EarthScope results for Alaska because it can inform the geodynamic models, and also those observations can create, like analyzing those can create hypotheses to test. So again, we're at the northern boundary of the Pacific Ring of Fire. And this is like, I don't know, it's like a rendering. But anyway, on the west, we have ocean subduction in the Aleutians, and then beneath the mainland, ocean continent. And here are the Holocene volcanoes plotted from the Smithsonian database. So along the Aleutian-Alaska arc, also in southeast, and then also in the interior. And I wanted for folks that are new to the area, I wanted to highlight a couple previous synthesis volumes, especially like the massive DNAG Geology of Alaska volume. I'm sure more senior people are like very familiar with this, but if you're new to the area, it's just a huge synthesis of like just geology and seismic data constraints like all over Alaska, and with a large collection of compilation maps with the actual articles. There was after that there was a AGU monograph 179 in 2008, active tectonics and seismic potential of Alaska. And then again, bringing us sort of now post EarthScope, we recently published this tectonics and seismic structure of Alaska, Northwestern Canada, EarthScope and beyond. That's the name of the volume that I'm going to like introduce today. And I want to point out that it's AGU Wiley, and so you can if you go like Google Scholar, get any of these papers, logging in through with your AGU membership, you can download any of the papers. So even though it's a monograph volume, you don't necessarily need the whole thing. You can get the papers individually with your AGU membership or your institution membership. Okay. And so what we did is there's 22 papers in the volume. We divided it into 4 parts. The first one is an introduction to EarthScope networks in Alaska. So again, if you're kind of like, what was EarthScope? Like, where were the networks in Alaska? What was the duration? Part 1 is good, has a good synthesis papers on that. Part 2, synthesis studies of Alaska, Northwestern Canada from the crust to the lower mantle. So as that is sort of from the crust downwards, spanning the entire state. And then Part 3, Aleutian Alaska subduction properties, interface structure and dynamics. So these are papers that really focus on the interface, sort of east to west. And then Part 4, the transform and oblique system. These are a bunch of regional studies that range from seismic studies, geologic studies that look at these oblique systems from the plate boundary corner all the way north to the northeastern Brooks Range. And so I'm just going to pan through the sections, and this is again, there's 22 papers, most of which are not mine. So I'm just going to highlight them and just make you aware of these compilations. And so Part 1, so here's a plot. This is from Chapter 1, EarthScope networks in Alaska, Northwestern Canada. And so on the left side, and I think I flipped it from the order in the book, but anyway, so on the left side, these are the seismic stations. So before EarthScope in the upper left, the EarthScope array in the middle left, and then on the bottom, a lot of infrastructure remains. So those were the broadband sites, post EarthScope as of 2023. And then on the right, these are continuous GPS before EarthScope on the upper right, middle EarthScope plate boundary observatories. These were continuous GPS, and then 2023 post EarthScope PBO stations that remained for the GPS. And then Part 2, again, so there's 7 papers here. And so a review of, I'm going to highlight some pictures from a couple of these, but I can't fit them all. We only have 10 minutes, but there's like a review of a decade of seismicity. And again, in part 2, we're looking at the from the surface. So seismicity, an updated crustal fault model, geodetic observations, and then we start to get a little bit deeper into the crust and continental lithosphere, a synthesis of the seismic structure in mainland Alaska, and then there's a really great synthesis for Northwestern Canada. And then we go deeper into the mantle, looking at slab geometry, and then there's a geodynamic synthesis. And so just highlighting a couple images. This is the chapter 3, decade of seismicity, Alaska seismicity from 2013 to 2022. And those are the study, the focus regions. On the right, we have the updated the crustal fault model for the 2023 National Seismic Hazard Model for Alaska. And again, I just grabbed some images just to let you know what's there. There's also this is from chapter 5, the geodetic observations of tectonic deformation in Alaska and Western Canada, the EarthScope revolution. And then this is chapter 7. This is the synthesis of seismic studies and the constraining the structure, origin, and deformation of the lithosphere in Northwestern Canada, and parts of Alaska in the corner constrained there as well. And then coming back to Alaska, so on the left, there's a synthesis of a range of seismic studies for looking at analyzing these studies and doing the cluster analysis and identifying or just sort of having with this cluster analysis identifying these seismic domains within the state, within mainland Alaska, for the crust, and then the uppermost mantle. And then on the right is a partner study using vote maps to see where there is agreement between a range of seismic studies on the location of a fast velocity results. So on the right, for example, this is colored by agreement of seismically fast regions. And so that's not data showing the slab, but it's where there's agreement where there are seismically fast signals. And so perhaps there is a slab that's folded. This is pretty new so perhaps there's a slab that's folded over on the transition zone, possibly then impeding, and then as you go farther west, possibly laying flat. So this would be deeper than what we're seeing in slab 2. Then this is a geodynamic synthesis. So this was I'm a lead on this one. And so again, all of these ones, especially in this section, a lot of them have a review component to them. So here I'm bringing in constraints from geodynamic models that are relevant to subduction dynamics. And there's a range of models. There's a cartoon in the upper left that goes through that. I want to highlight a couple things. This didn't render right, but the lower right is different features that can lead to flat slab subduction, many of which all occur in Alaska. I know there's this plateau that's subducting and colliding, and so it's sort of a given, oh, it's a flat slab because there's a plateau, but no model has actually evolved a plateau of the given size of Yakutat and shown that it is what's making the slab flat. Generalized models show that depending upon the size of that positive buoyancy anomaly, you can get a slab subducted without going flat. If it's depending upon that ratio, it can go flat. And so probably that is what it is, but there actually hasn't been a model to show that hasn't systematically shown that given the plateau size that we expect for Yakutat and everything else going on, that it is it. And so another thing, you can also get a flat slab if the slab's curled over on the transition zone, which may be happening now in Alaska. And so again, there's still so much to understand about the first order subduction dynamics here. And so constraints that we're kind of going over now are really essential. And so these go over, synthesize a ton of geodynamics literature on that. And so and again, I've spent a lot of time thinking about the slab edge dynamics. And so that's just that little pod would be where the flow results from one of the models that I ran with the purple envelope showing where you have upwelling due to these 3D dynamics that could be explaining why the wrangles are there. And I don't really have time to go into that, but those in the middle, this is a slice at 100 kilometers, the bright yellow orange stuff, that's vertical velocity. And this was from the Jadamec and Bill in 2000, 10 slab E115. But with EarthScope, from those results, it looks like the slab edge thing is this way more. And so I imagine running another model, if the edge was more this way, it might shift that upwelling south a little bit more and better fit to the location of the wrangles. But this mechanism, maybe this slab edge dynamic mechanism may be leading to the wrangles in general. Happy to talk about that more. The part 3, again, the subduction interface properties, a whole range of studies. I can't go over them all here. Again, I'm just going to highlight a few. Here, this Aleutian Alaska subduction zone interface earthquake recurrence model from geology and geodesy in the upper left, tectonic tremor observations, mostly focusing on the southeastern part of Alaska. On the right, there's a synthesis, a study synthesizing like the characteristics of the Yakutat Plateau, and then a simplified plateau anomaly was put into the Alaska models, looking at that effect on the deformation. Chapter 16 is implications of earthquakes for the megathrust coupling, and that's another model looking at seismicity in the vicinity of the Shumagon Gap. There's also offshore studies looking at MCS, or like reflection data. Again, offshore the Alaska Peninsula. And then this last section, so we had done like we'd done like sort of the broader state, sort of from crust to downward, and then we looked at the subduction interface along the length. And then this last section is really focusing on transformer oblique systems like convergent and some kind of strike slip, but oblique systems from the corner, just systematic studies for regions up to the northeastern Alaska. And I'm probably just about out of time. I feel bad I can't show them all here, but not all of these are particularly relevant for just the mega, just along the subduction zone. Those are volcanoes, but some of them might be relevant for some of the interior volcanoes. Chapter 17, oblique contraction along the fastest. This is like the transform boundary along Queen Charlotte Fairweather Fault System in Southeast Alaska, and looking at uplift, and then there's a compilation study and like synthesis looking at possibly the effect of upper plate controls on localized arc magnetism, more from a historical compilation. So I know it was a lot, it's a ton of papers, 22, but I just want to make everyone aware of this, that there's a lot of really great synthesis work, and a lot of them, especially in the beginning, have a lot of review information. And so that's basically it. It was a lot. And Jeff's here, and there's other authors sort of from different chapters in it here too. So and yeah, again, that's it.
Thank you. Any questions while we transition to our last talk?